our review for Chapter 3 of our text, and today we're looking at optimization, which is an application of finding max and min of a function. This review is intended for the students who can't be here in the classroom, but I hope it is useful to everybody. Alright, let's look at some examples of optimization and explain how it works. Alright, so here's an example of an optimization problem. We have a box with a square base, we have a given volume of 32,000 centimeters cubed, and what we want to do is find the dimensions of the box that minimize the amount of material. Alright, so hopefully you can see that this is a max or min question because they use the word minimize. So I have a process that, if you follow, will help demystify, just like with related rates, some of the challenge of these optimization problems. And the first thing I always recommend doing is just draw a figure to get an idea of what's going on. So here I have a box with a square base, and we would want to make sure, is this an open top box or not? I just forgot to write that down. Okay, so it looks something like this, but it's open on the inside. Alright, now let's put some variables down. We know how it has a square base, so these sides can both be x, and it's got some sort of height. Let's call that y. And I know that the total volume of this is 32,000 centimeters cubed. Okay, so I know that. So there's a pretty good image of what we're dealing with here. Alright, now the second part of this, what we want to do for part 2, is we want to figure out what we're trying to optimize. So what is the question actually asking for? And so as I read the text, I see that we want to minimize amount of material. So I'm trying to minimize the amount of material. So for a box, how much cardboard are we using on this box? We want to minimize surface area. And so it might be a good idea to try to characterize what the surface area of this box is. So if I'm thinking about surface area of this box, that means that I have to calculate the area of all these faces and then add them all together. I know that the base is going to have area x by x because it's square, and then I know each of the sides is going to have an area of y times x, and I have 4 of those. So that's 4x times y. And this is the function that we're trying to minimize. Now the problem is that it's a 2-variable function right now. You have to give me an x and a y. So this is where we use what we know to create a 1-variable function. And so what I know here is that the volume, which is 32,000 centimeters cubed, well, I actually can calculate the volume of a box because it's the area of the base, which is going to be x, times the height, which is y. So I get x squared y is the volume of this box. And I know that that's going to be 32,000. And so what that allows me to do then is solve for y to be 32,000 over x squared. I also can put some restrictions on x and y. I know that they both have to be bigger than 0. That just makes sense. Okay, so once I do that, I can substitute in, I'll call this s of x, which is not a function of x at the moment. But since I have a substitution for y, I can substitute that in and get a function of x. So it's x squared plus 4 times x times 32,000 over x squared. And so as this simplifies, I get 128,000, which is 4 times 32,000 over x. So there's the function that I'm trying to minimize. Okay, so remember, we are trying to minimize the surface area, so we want to find the min value of s of x. And it might be a good idea to go ahead and bring these together. So if I multiply x over x to get a common denominator, end up with x cubed over 128,000 equals x. And that's what I'm trying to minimize. And the way I do that is by what? It's the same process that we use to find increase and decrease. We're going to take the derivative, find a critical point, and then use either the first or second derivative test to determine whether it's a max or a min. So find my derivative. And actually, now I'm thinking about it, it'd probably be easier to take the derivative of that expression, and I get 2x minus 128,000 over x squared, right? Because this is going to be, because that term is 128,000 x to the negative 1 power. So that becomes negative 128,000 x to the negative 2 power, which is what we have here. So I'm going to go ahead and bring these together, getting a common denominator. And I need to find my critical points. Now the critical points, remember, come from the numerator equaling 0, which would give you the horizontal tangent lines, or also where the denominator equals 0, which can give you your vertical tangent lines. Here we have at x equals 0, we have a problem. But that, I mean, what kind of box would you have with a 0 by 0 square base anyway? So we know that that's not really going to be an issue. We just need to solve 2x cubed equals 128,000. So I get the cube root of 64,000, which would be 40. So 40 is a critical point. Now, is that a max or a min? I'm going to tell you it's a min, but we could test it quickly like this. We take in 40, we have s prime, we plug in some test values, so something less than 40, how about 10? Something greater than 40, how about 1,000? And when I plug them into my derivative, either here or here, those are the same thing. When I plug in the value 10, I get negatives, and when I plug in the value 1,000, I get positive, which tells me that my graph was decreasing and then increasing. So by the first derivative test, x equals 40 is a local min. And so there I found my minimum. All right, so lastly, we want to summarize what we said here. So what I know is the box of minimum surface area with volume of 72,000 centimeters cubed has dimensions 40 by 40, that's the base, times some sort of height. And we need to figure out what that height is. So we need to go back and find my y value here. And if I remember, my y value is 32,000 over x squared. So at that point then, we just need to plug in, we just need to do some scratch work and say 32,000 divided by 40 squared, and you end up with 20. So my box is a 40 by 40 by 20. And these are in centimeters, right? Okay, I hope this makes sense. Guys, these optimization questions can be tricky sometimes because, well, they're word problems and they require of us to be able to generate a formula, for example, in this question of surface area. But if you follow these steps of drawing our figure and then characterizing what we want to optimize, finding a one variable function, maximizing or minimizing that one variable function through derivatives, and then finally summarizing your results, if you follow that process, I think it'll make these a lot clearer. If you have any questions on this, I'd be glad to help you. Good luck in your studies, and thanks for watching.